Hello everyone. We are going to be starting with linear equations and linear algebra, and I will be looking at two sections here. Section 1-1, which is system of linear equations, and then section 1-2, which will be row reduction and echelon forms. The topics I'll be covering is what is a system of linear equation, which we call as a linear system. How do we find solutions of a linear system, relationship of linear system with matrices, row reduction, and echelon forms. So let's start with, first of all, what is a linear equation? Now, a linear equation in variables x1, x2, xn is an equation which can be written in the form of a1 x1 plus a2 x2 plus an x sub n equals b, where b and these coefficients a1 to an can be real or complex numbers, and they're usually known in advance. For example, 9x1 minus 4x2 plus square root 7 minus x3 equals 0. So this is a linear equation where we have three variables, x1, x2, x3. Then second example, y minus 5x equals 6. That's equation number 2 with two variables, y and x. So the question is, what is the significance of a linear? And because equation definitely means simply an equal with two expressions on either side of an equal sign. So linear has a very specific meaning. Let's look into that. Now, to explain what is meant by a linear in a linear equation, we'd like to see some examples of not linear. For example, x1 minus x2 times x3 equals 5. In this one, notice there's a product, and that is not allowed. It kind of looks a little different. The second here, this equation in this slide, a minus square root 5b equals 6. So you're having a square root of the variable b. Not possible. And then we have y equals sine x. We're having a transcendental function, which is basically like the coefficient. That's also not allowed. So what we see here is a linear equation does not involve any products or roots of variables. So we cannot have things which are being shown in equation 3 here. Then all variables have exponent 1, or the highest power of the variable is 1. What's the, exponent here? You have b to the power half. Not possible. Because every variable has to have exponent 1, or the highest power is also of the variable is 1. We can say that. Now, all variable coefficients cannot be transcendental functions like trigonometric, logarithmic, exponential, or any combination. That is also not allowed in a linear equation. Okay, so let's start with system of linear equations. We say a system of linear equations or a linear system is a collection of one or more linear equations which are involving the same variables. For example, let's look at the linear system given by equation 6. This is a linear system. I'll be using the abbreviation LS. 5x1 plus 3x2 equals 9. 2x1 minus 4x equals 2 equals 14. It is a linear system with two linear equations and two variables, x1 and x2. Similarly, we have a linear system which is given by this equation 7 here, 6x1 minus 10x2 equals 0, minus 3x1 plus 5x2 equals 5. So this is a linear system, again, which has two variables and two equations. And finally, another example of a linear system, which is 4x1 plus 10x2 equals 14, minus 6x1 minus 15x2 equals negative 21. Okay, when I say x1, I basically means x sub 1. It doesn't matter whatever you call it. Okay. Very important. these linear systems are given, but we need to have some information out of them. And that information is in the hands of the solution of the system. That means what values the variables can take, and both the equations in that linear system are happy. In the previous slide I'm talking about. So a solution to a linear system is a list of numbers. A list means it's very specifically how the values appear. And these list of numbers are such that it will make every equation in the given linear system to be true when these values S1 to Sn are substituted for the variables in the appropriate linear system. And when we look at the set of all possible solutions for a given linear system, we call it to be a solution set of the linear system. So we have learned what is a linear equation, what is a linear system, and the solutions. Now let's start with examples, and we will go back to this slide, and I'm going to pick up these three linear systems and see what are the solutions of these three linear systems. One at a time, I'm going to pick them up. Okay, let's start with this linear system given by 5x1 plus 3x2 equals 9 and 2x1 minus 4x2 equals 14. Now, I know all of you guys know how to solve it, so the best way to do is, cancel one of the variables. So I'm going to cancel here x2, makes my life simple, easy. So I'm going to multiply that. This one says equation 1, this is equation 2. I'm going to multiply the first equation by 4, the second equation by 3. So what I'm getting is 20x1 plus 12x2 equals 36. 6x1 minus 12x2 equals 42. And then we add these two equations, we get 26x1 equals 78, x1 to be 3. So we got one of the values of the variable. And then we plug this value of x1 in either equation 1 or equation 2. I'm just going to plug it in. So plug x1 equals 3, say, in equation 1. What do I get? 5 times 3 plus 3x2 equals 9, or 3x2 is 9 minus 15, 3x2 is negative 6, x2 is minus 2. So the solution for this linear system is 3 and minus 2. And this solution will satisfy not only equation 1 but also equation 2. So this linear system has only one solution. How will it look like graphically? So let's look at the graphical representation of this linear system. So you will notice this is how the system looks like. x1 is representing by horizontal axis and x2 is the vertical axis. So this point where they both equations meet, this is 3 and minus 2. So whenever a linear system has one solution, which graphically means that the equations which are involved in that linear system are all going to be meeting at a point. Okay, so let's look at one more thing here. So when we were solving this linear system, we multiplied this given linear system by some constants to get a new linear system. So this linear system and this linear system are basically equivalent, because when you get the solution, you plug it in this linear system or you plug it in this linear system, the one which is given, it's going to still give the same answer. So in a scenario where we two linear systems which have the same solution set, they are called equivalent linear systems. Once again, two linear systems are equivalent if they have the same solution set. And this is basically a repeat of the previous slide I just talked about. Remember, the solution was what for this one? 3 and minus 2. It not only satisfied this, but also this. You can check it out and you will see that this solution is a solution to first linear system and as well as the second linear system. Now, let's go ahead and look at another linear system and see what kind of a solution that this linear system has. Now, this one I would like to get rid of, say, x1. What I'm going to do, multiply this by 1 and the second equation. So let's say this is equation 1, this is equation 2. Multiply the second equation by 2. We get 6x1 minus 10x2 equals 0 and minus 6x1 plus 10x2 equals 10. So when you solve, the left hand side on the equal sign is a 0, but the right hand side gives me a 10. Oops, that doesn't sound right. How can an equal sign have two different terms on either side of it? Not possible. So what basically this means is this linear system has no solution. And graphically, this basically are two parallel lines. Okay, so this one is equation 1. By the way, this is equation 2. This is x1 and x2. So what we have learned is that if you have a linear system where you have no solution, graphically it is two parallel lines. Okay, let's look one more linear system and see what we get. This one, let this be equation 1 and second be equation 2. I'm going to get rid of, say, x2 over here. Multiply this by a 3, this by a 2. What do we get? 12x1 plus 30x2 equals 42. The second equation gives me negative 12x1, negative 30x2 equals negative 42. When you add these two, you get a 0 equals 0. Oops. It's just identical. So in this scenario, we say that this system has infinite solutions. You give one value for x1, automatically you will get a value for x2. So basically giving any values to x1 will give you corresponding x2s. So this is a scenario of infinite. Graphically, what it means is it's one straight line. And it is basically multiples of a one straight line. Okay? So let me show you also which is that common line which you multiply with constants to, which will give these different versions of that equation. So let me just, so this is x1 and x2. Okay, let's look at this equation 1. Sure, let me show over here. If I multiply half to equation 1, what do I get? Half of 4x1 plus 10x2 equals 14. I'm going to get is 2x1 plus 5x2 equals 7. Okay, let's look at equation 2. You see negative 3 is common. I'm going to multiply the second equation by negative 1/3 equation. Negative 1/3 equation 2. What do we get? Negative 1/3, negative 6x1, negative 15x2 equals negative 21. We are once again going to get 2x1 plus 5x2 equals 7. So these equation 1 and equation 2 in this slide are basically multiples of the equation 2x1 plus 5x2 equals 7. So when you have a linear system, what we have learned till now is either you will have one solution, no solution, or infinite solutions. So I'm going to put them together in a little slide for us. A system of linear equations, as I just said, has no solution, exactly one, or infinitely many solutions. Now this system, we're going to start with some more terminology, is said to be consistent if the linear system has one solution or infinitely many solutions. And if a linear system has no solution, we say it is inconsistent. Okay. Now we are going to see a relationship between the linear system and matrices. Remember, matrices are nothing but rectangular arrangements of rows, and it's an arrangement of rows and columns. So you'll see how a linear system can be written as a matrix. So when you look at a linear system, you can see that it can be nicely written in a rectangular arrangement called a matrix. What we do is, let's pick up this equation, say x1 minus 2x2 plus x3 equals 0, 2x2 minus 8x3 equals 8, minus 4x1 plus 5x2 plus 9x3 equals minus 9. So I have a linear system, and LS is what I will be using as an abbreviation for linear system, with three variables, x1, x2, and x3, and it has three equations. So what we basically do is, so if you look at this equation here, I can write, if I only look at the left-hand side of the equal sign, okay? So if I remove the variables x1, x2, and x3 and just keep the coefficients, and then just put them and exactly just remove the variables and the equations in the same proper place. So this one will be equation 1. This is going to be equation 2. This is equation 3. So which will basically become the 3 rows of the matrix. Just removing, I'm only looking at this part, guys. I'm looking at the left-hand side, okay? Just the left-hand side. And what we do is we kind of remove the variables and just let this be where they're positioned. So the first equation now is going to be the first row. It will be 1, negative 2, and 1. Equation 2 is now going to be the second row, 0, 2, minus 8. And I'm making sure that I am keeping in mind the x1s, as I'm assuming my x1 will be the first variable. So the x1s, as I said, are going to be represented by the first column. I'm making sure all the x2s are at the same place, and that's how I'm looking at it. So the x2s are together, minus 2, 2, 5, and the x3s are 1, minus 8, and 9. So what we basically do is, before we write the matrix form of the left-hand side, we kind of make sure that all the x1s are written first, the x2s are written second, x3s are written the third. And once you follow the convention for the first equation, you make sure the other two, or how many ever equations are there, they follow the same convention. Because when you write x1 and then you put x2 over there, that's not right. Okay. For example, let me show you here. So if I have an equation, say 3x1 plus 4x2 equals 3, and then I have x2 minus x1 equals 2. Now, in this one, when I want to write the matrix form, I have to make sure when I'm writing it down before the matrix form of the left-hand side, I'm going to write down the x1 beneath an x1 and x2 beneath the x2. So this one, I'm just going to rearrange so that when I write the matrix form of the left-hand side of this linear system, I won't make any mistakes. So it's minus x1 plus x2 equals 2. So this one, when I write down the matrix form, I'm looking only at the variables. I'm not looking on the right-hand side of the system. So that is going to be 3, 4, minus 1, 1. Okay, so when we write down this matrix from the linear system, only of the variables, this is called the coefficient matrix. Okay. In other words, when we are trying to solve these problems, all the constant terms are on the right-hand side. Notice all the constant terms are on the right-hand side of the linear system. That's very important. If I'm going to write down the matrix of coefficients or coefficient matrix, all the constants have to be on the right-hand side of the equal sign. Okay. Now, what is an augmented matrix? That's another More notations I'm going to talk about, so that's the next slide. An augmented matrix is the linear system is a coefficient matrix and includes the constant from the right side of the equation. So notice from the previous slide, we had 0, 8, negative 9. I'm making sure these equations are exactly the way I have kind of written down. So 0 is for equation 1, 8 is for equation 2, negative 9 is for equation 3. So this is how we write it down. So the very last column, so if you have an equation, linear system, where you include the constant terms which are on the right hand side of the equal sign, they always will be put in the very last column, and that matrix is called an augmented matrix. Okay, let's do some practice for this example which I did here. So remember I had picked up the example. Let's go back here. 3x1 plus 4x2 equals 3, and I have written as x2 minus x1 equals 2. So when I want to write down the augmented matrix, before I go ahead and do that, what I'm going to do is I'm going to rearrange these second equation x1s and x2 so that I do not make a mistake here. So 3x1 plus 4x2 equals 3 minus x1 plus x2 equals 2. So when I write down the augmented matrix, remember I'm writing down the augmented matrix. That means the matrix which has all the numbers, no variables, no equal sign. So when I start, I make sure, okay, how do I want to proceed? So I'm making sure my x1 is first, x2 is second in the linear equation, and all the constant terms are on the right hand side of the equal sign. So it's 3, 4, and then just to make myself a little easy, I've put a line to show, oh, this is the augmented matrix, and I write a 3. If you don't want to write the vertical line, that's fine too. Then we write on the second equation, minus 1 row for the matrix, augment 1, 1 and 2. Now let's do one more example, and then I will let you guys practice. I have them for you on the next slide. Okay, so suppose I have an equation like this. Say x minus y plus z minus 3 equals 1. X plus z equals 2, and z equals, or z minus 6 equals 5. So when I have this linear system, I said, can you write an augmented matrix? Notice there are sometimes constants are available on the left hand side, so you have to kind of write it down in the proper form. So this one, I'm going to write it in a proper form, one constant term on the right hand side. And I'm going to write this as x minus y plus z equals 1. And I take the constants on the other, 1 minus 3 is a 4. Then x, and there is no z, y, so I say x plus z equals 2. The second equation was kind of working nice, so it is plus 0y. Think of that. And there is no x's and y's, so it's only a z, but the constant term has to be taken here. 6 plus 5 is 11. So when I want to write down the matrix, the augmented matrix for it, so my life is easy. It's 1 minus 1, and this is how I want. So I made sure the linear system is written in a form where the first equation, and I'm also telling how I want the variables to be shown, and that sets a precedence for the next set of equations. So first column is being represented by the variable x, second column is being represented by the variable y, third column is being represented by the variable z. And then, sometimes you will see a dotted line, sometimes you won't see a line because I'm talking of an augmented matrix. The augmented matrix, the first equation has a 4 on the right hand side. Now the second one, 1, 0, 1, 2. The third one is a 0, 0, 1, 11. Okay, now guys, you will practice. So I have written down a linear system, and you will write down the corresponding coefficient matrix and the augment matrix. Okay, I've also given you another practice for you to do is I give you an augment matrix, write down a linear system. So I'm going to take one simple example. So it is 1, 2, -3, ... 0, 0, 1, 1, 4, 1, -1, 2, 1. Now, if this was an augment matrix given to you, you will write down the corresponding linear system. I can use this as x1 plus 2x2 minus 3x3 equals 0. Now this has only two variables, x2 and x3. I'm going to write this as an x2 plus x3 equals 4. And the last equation, last row of the augment matrix will become the last equation of the linear system, corresponding linear system. So it will be x1 minus x2 plus 2x3 equals 1. So go ahead, guys, work on these three augment matrices and write down the corresponding linear system. Now, let's go ahead and solve a linear system of three equations with three variables. What I'm doing is, now we all know how to do these kind of problems, but what I'm going to be showing you in the next few slides is, as I'm working on applying the elimination procedure to this linear system, simultaneously I will be writing down the corresponding augment matrix of it. And you will see what happens is, what we do in the linear system, it will be also told in the form, when you're solving this linear system by applying this elimination procedure, you will see how the augment matrix also performs, and then we go from there. Okay, let's start. So all the work has been done. I'm just going to go over through the steps. So this is the linear system and its corresponding augment matrix. Notice in this one, I did not write, the line. So this matrix is, this is the augment matrix. As I said, you can have, so once you get comfortable with the meaning of an augment matrix, that is the very last column is nothing but the column of constants, you just go ahead and solve it. So just let's start with the elimination procedure. Now what is that is we all know how to solve, try to get a linear equation with two variables and two equations. So in this one we notice we have three equations and three variables. The second equation already has two equations and two variables. So we can make one of the other equations also as two equations with the same variables as the second equation. So what we do is we multiply the first equation by 4 and then add it to the third equation, and the results are placed in the third equation. So as a result, the first equation is not changed, but the last equation, third equation, is changed. What you get is new equation is first and second are the same, but the new equation of the third equation becomes -3x2 plus 13x3 equals -9. Now you guys can do the math. Now, when you write down the corresponding augment matrix of this linear system is this. Now remember, this system and this system are equivalent linear systems. So that means these two matrices are equivalent augment matrices or equivalent matrices. Now in terms, so when I did the computation to get rid of the x1 variable in the third equation, we were doing the things we have learned previously in our other classes. But in terms of the matrix notation, what is really going on? So this matrix is, say, R1, row 1, row 2, and row 3. So what we are doing is we are multiplying the first row by 4 and adding it to the third row, and the change is being put in the third row. This is the notation. Like the input is 4 times R1 plus R3, the change is going to R3. That's a very important relationship. So from now on, keep in mind that if you want to make the change in the whichever rows we are working on, that should always show after, that is the output, and that's why I'm doing. So we say we multiply first row by 4, add it to the third row, and we get R3, which basically is as if you're solving this linear system on the left-hand side of the slide. Okay, so this is the corresponding matrix after we have done this computational work. Okay, now we know how to solve the last two equations, and basically as we solve it, we will write down the corresponding matrix, augment matrix of it. Okay, let's look at this one. So notice the last equation, I need to get that, yeah. In the last equation, the second equation has 2 common. So I can multiply the whole equation by half and there will be no change to the system, isn't it? And similarly, so what we do over here is we multiply the second equation by halves so as to get a 1 for x2. And in terms of matrix notation, what is going on is we are multiplying the second row by half and the answer goes to row 2. And so when we did the work on the linear system, this is the kind of equation we are getting. Its corresponding augment matrix is this, which also we could have got by doing this row operation. Okay, moving forward. Now, remember we have to solving for this, our main goal is to find a solution to this linear system. In other words, we want to find the value for x1, x2, x3. So now we're coming to a scenario where we can cancel one of the variables in the last two equations. So let's go forward and work on that. So in this linear system, I want to get rid of the x3. So let's show back here. So I can get rid of this x2 variable by multiplying. So what I'm doing is I'm multiplying 3 to equation 2. Remember, this is equation 2. And adding it to equation 3, which is this. When you multiply 3 times equation 2, add to equation 3, in what are we going? And the results are placed. So what we do over here is, so this is what we're doing. We're doing 3x2 and then solving for x2 over here, x2 for x2 and x3 in the last two equations. So 3x2 minus 12x3 equals what? 4 is what? 3 times 12 minus 3x2 plus 13x3 equals 9, negative 9. Cancels out. What are we left with? 30 minus 13. Okay, let me just clean this up. So this was minus 12. Then this negative cancel out. So minus 12 plus 13x3 gave me x3 equals 3. So when we solve this one, we got x3 equals 3. And that's what is written over here. We solve this and we get x2 minus 4x3 equals 4, x3 equals 3. So we can plug back. So now this is a linear system. And we can easily solve for x2, x1. Let's go back in terms of the matrix notation. What did we do in the matrix notation? We added 3 times the second row to the third row, placed the results in the third row. And this is how we write it in a very concise form, that 3 times R2 plus R3 goes to R3. Remember, the first 2 rows are not changed. It's only the third row which is changed. Now, as we can see this linear system, we can easily do back substitution and solve for x1 and x2. Now, the values, x3 is already 3, x1 is 29, x2 16. You can easily do the math here. Now, the above augment matrix. Now, this is important. Now, I'm going to introduce more terminology here. Let's look at this augment matrix, which we have got after doing all our little computational work. This augment matrix is said to be in echelon form or row echelon form. Now, for a matrix to be in this form, there has to be 3 properties. let's look at what these properties are. And this is which is section 1-2, which I'm talking about now. And some of the things which I've also done are also coming from section 1-2 here. So the echelon form, guys, is what are the three basic properties: that all the non-zero rows are above any row of zeros. In other words, if you have a bunch of zeros rows, they all go at the bottom of the matrix. Then every leading entry. Now, leading entry means a leftmost non-zero entry in a row. Of a row is a column to the right of the leading entry of the row above it. And then all the entries in a column below a leading entry is 0. Okay, so we have all these words and sentences. Let's look at examples. Okay, so it says, for example, I'll give you an example here. So if I have a matrix, it's for any matrix echelon form, remember. If I have a bunch of zeros, so suppose I have 4 columns and I have a bunch of zeros. Now, if there was a non-zero row, so a non-zero row, and there's a leading entry here. So this is a leading entry, and I'm going to draw it by a black filled rectangle. And this one is the first non-zero entry. Then anything after that in that row can be any element, we don't care. Before that is a bunch of zeros. So if it is a leading entry, that means the first non-zero, leftmost non-zero in that row, that will have a bunch of zeros beneath it. Now, if there is another non-zero row, and it is above this above this third row, the third row from the bottom, and it has a non-zero entry, it has to be on the left side of it. Suppose the non-zero entry is here. So this is the first non-zero entry. Now we don't care what is after that. The only thing is, if it is the first non-zero entry, everything below is a bunch of zeros. So this is a leading entry. The next leading entry is the next non-zero row, and that leading entry will be to the right of it, and that's the leading entry. And in the places where there's leading entry, all the values beneath this has to be a bunch of zeros. Okay. Now let's look at some examples. So here we start with, so the first thing is, as I said, the filled squares or rectangles, whatever you want here. So it's a nice little square for us. So this is the non-zero entry. Then every element beneath that leading entry has to be 0. And anything after that will be stars. We don't care. The stars can be any value. It can be a 0. It can be a non-zero value. We do not care. So then I'm starting from the top. We go to the next line. Is having a non-zero entry? Oh yes, this is this little black filled square. That's the non-zero entry. It has to have a 0 beneath it. Whatever is next to it, we don't care. Then when we look at the next non-zero row, that has to have a leading entry to the right of the previous leading entry. And we are done. Similarly, this example, number 2 and number 3. Okay, that's an echelon form of a matrix. A row-reduced echelon form, remember, row-reduced, is one more step. It's first of all an echelon form, and then wherever there are non-leading entries, every leading entry is a 1, and every column which has a leading entry, anything above or below has to be a 0. Okay, so it is written in the next slide. What are the requirements for a matrix to be in a row-reduced echelon form? That all the non-zero rows are above any rows of zeros. Every leading entry of a row is in a column to the right of the leading entry of the row above it. Now these two are basically talking of the echelon form, guys. Okay, and every leading entry in a non-zero row is 1. And all the entries in the column which has the leading entry above and below is a 0. So let's go back over here and this one. So what would be the row reduced echelon form? It will be 1. This does not matter. It can be a star. Because it's 1, everything has to be 0. This is 0. This is 1. Now, because this is a row reduced echelon form, this will be a 0 now. Okay? This will be at this point anything. So then we go 0. So this one doesn't matter because it's not a leading entry column. Now, because the third column is a leading entry, it has to have a 0 above and below. And also we see that this is a non-zero row where the leading entry is in the fourth column. So this is 1. Next to it, we don't care, but if it is in the row reduced, now this is the row reduced, guys, echelon form. That means these two stars have to be 0 now. This is 0 and this is 0. Okay? So the slides here, this slide number 23 basically is giving us all the row reduced echelon forms of the echelon forms given earlier. Okay. A very important observation. An echelon matrix or a reduced echelon matrix is the one that is in the echelon form or in respectively the reduced echelon form. Okay. So remember we had solved the linear system before and we had got to an echelon form and then we went back to this. Now, and I said we can do back substitution and get the values for x1 and x2 and x3. What we could have also done was, from here we went, in this linear system, remember, we went back and did back substitution and got these solutions for the rest of the variables x1 and x2 because x3 equals 3 was a solution. We could have gone further and this matrix can be reduced to a row reduced echelon form, and when we do that, that means this one should be a 0, this should be a 0, this be a 0. So in other words, we had to do 3 more operations and to get these 3 zeros, and as a result there will be a new change in this matrix. So let's go ahead and do that. Okay, I'm going to write down the matrix which was here. Okay, I'm just looking at the augment matrix forms and guys, I'm going to just work on that. Okay, so this was the augment matrix. In this one, I want to make this 0 and column 3, row 2 and row 1 values to be 0. Okay, so this is basically, these are the two values I want to make to be 0. What am I going to do? I'm going to add 4 times the third row. I think it's a -4. Let's check. What was the value here? Oh, it's a -4. I forgot. Yeah, this is a -4, guys. So I want to make this to be 0, this to be 0. So we're going to multiply the third row by 4 and add it to the second row. The changes is going to be made in the second row. So it's 4 times R3 plus R2 to 2. And similarly, I'm making the change in the first row. What we can do is we can add -1 times the third equation, add it to the first equation, and then the answer. So what do we see? When this happens, we get x2 to be 16 and x1 minus 2x2 to be 0. The corresponding matrix is this. Now we have to make this to be 0. Or how we can do that? In terms of the linear system, we can multiply this. We can multiply the second equation by 2. That makes it 32. And add to the first equation, what do we get? x1 equals 32. or in terms of the augment matrix, it's going to be 2 times R2 plus R1 goes to R1. So what are we getting? We are going to get 1, 0, 0, 32, 0, 1, 0, 16. Oh, no, minus 3. Oh, I made a change, guys. So there it is. There's a typo. We could see that. This should not be a 0, guys. This should be negative 3. There's a typo, guys, here. This is negative 3. That's why I made a mistake. So x1 is 32 minus 3, which is 29. So this is 29, guys. And 0, 1, 0, 16, 0, 0, 1, 3. Okay. So here are your results. x1 is 29, x2 is 16, x3 is 3. So what you see is when you apply all this, when you do the row reduced echelon form from the original augment matrix when we started, the final answer, if you want to get all the values for x1, x2, x3, you will get is the coefficient matrix to be an identity matrix, if you remember that from your matrix video. Okay. Now, moving forward, these elementary row operations. Now, notice what we were doing when we would all the time we were doing operations which were on the row. These are called the elementary row operations. What simply means is you replace one row by the sum of itself and a multiple of another row, which is called the replacement row operation. Interchanges, it doesn't matter which of the equations you want to place first. It will still not affect the original, the solution. And scaling is that we can multiply or divide by a non-zero number, especially if you're doing, or let's say multiplication. If you're multiplying by all the entries in a row by a non-zero constant, it still will not be affected. Now, two matrices. Now let's look at some further information here. The two matrices which are called row equivalent, if we have a sequence of elementary row operations which will transform one matrix to another matrix, these things are, these row operations are reversible. In other words, if I'm interchange two rows, I can further interchange and get back to the original way the rows were. And if the augment matrices of two linear systems are row equivalent, then these two systems have the same solution set. Basically, if you remember, let's go back over here. What I'm talking is, remember when we were moving from one linear system to the other linear system? So that this linear system, when we move to this linear system after doing these elementary row operations. So basically, this one is also representing the original matrix. So this one, we remember we were saying that these are equivalent systems. On the similar scenario, when two matrices are formed from by doing these elementary row operations, they are called row equivalent matrices. Okay. Now, the most important question for us in a linear system is the system consistent? That's a very important one. Is the system consistent? That means, does it have one solution, at least one solution? Then the second question is, if there is a solution, is it unique? Because remember, a system which is consistent means it can have one solution or infinite solutions. So the next question comes up, if it is there, is it a unique solution? So this is the whole theory about linear systems, guys. And the final thing, I would like to guys practice from the laybook, section 1. These are some of the questions I want you to practice. What is the most important thing is I want to practice when you do these. I would like you to apply the linear system, change the linear system into an augment matrix and reduce it into a row echelon form by applying these elementary row operations to arrive at an answer. So section 1.1, these are the questions. In section 1.2, only 1 and 2 I would like you to practice. Thank you.